Got some videos here to get your attention.
Oops.
Yeah, dude. Whoa.
Bring you some pictures that came in from Edinburgh. Now, these were on Friday, but this was the Scottish Widows building there. And just look at that snow coming off the roof there, and all those people.
Oh my God.
It's going. Here we go. Oh, nice. Thunderstorm. Woo! Woo!
Ma devi scuola, ja pussiš jau enkelt gurmieta. Šodien se nes nav uno stran siedu.
Valentine's Day 2007. Avalanche! Oh, how woo! I didn't realize what you were saying, honey.
So all those videos rather illustrate how dramatically rooftop avalanches can be. And we're going to see a couple of more of those. But this program, just so that you know, is one that we present to architects all over the country every year. I think last year we did over 100 presentations to building architects to educate them about the importance of snow retention. So the program that you're going to see now, the slides that you're going to see, just know that those are also presented in different educational forums around the country and primarily to architects. We're going to learn about the art and science of snow control and its effects, such as migration on rooftops of structures, and learn about the science of snow retention and proper specification techniques, as well as do's and don'ts involving product selection and site specifics. So hopefully, upon completion of this, you will understand better the history and methods of snow control on rooftops, You'll be able to explain when and where you should or shouldn't use snow retention devices, list the common misperceptions and the science behind snow retention, the common pitfalls of product selection and site specifics, how to value engineer snow retention systems without compromising system performance. You know, usually value engineering is one of those terms that we hear, and it means make something cheaper. And oftentimes when that's done, you also do it at the expense of quality. So that's not what we're talking about here. We're talking about doing it without sacrificing performance. Explain the proper selection and specification of snow guards. The 5 key takeaways, the first one is really for architects. Obviously, you guys are not specifying snow retention systems, but often in your markets, you are the guys who drive those decisions. So I'm sure that many of you are involved with building construction that was not architecturally specified. Keep in mind, this was designed for architects, but in most cases, you are the decision makers. You make the buying decisions. So hopefully, you'll be better equipped to do that after this presentation. Another takeaway is to use mechanical attachment and not adhesives. We're going to get into that. Snow retention being engineered. The whole concept of engineering the system to design the specific forces that are trying to make it fail on any given job. And you're going to understand why it's so important that snow retention systems are tested, and also something about warranties. An obvious question, why use snow guards? Well, a few reasons. To protect building occupants and pedestrians, I think that that's somewhat obvious. To limit liability. People in the US are sue crazy. There are something like 480,000 trial lawyers looking for work in the United States. And we happen to be a pretty sue crazy kind of society in the United States. And this is something that I run into as I travel around the world. People in other countries are amazed at how sue crazy we are in this country. Protect vehicles and equipment, protect landscaping, protect building and roof elements, and you'll see examples of all this, and to reduce maintenance costs. Another video here. This one was fairly recent. It was a couple of years ago in Plano, Texas. Those are vehicles, by the way, under there. This one was in China. You're going to see a vehicle come down this street. And the next one, the second one, watch closely. Again, it's going to play it in slow motion here. And then it's going to show you some of the aftermath. That's the vehicle, was the Land Rover.
Whoa, look at
That's
it.
incredible.
That's amazing. And the driver going by pretty slowly there. It's time to hit the gas. The other big danger, the ice. It's not just dangerous driving on it. It's dangerous parking anywhere near it. As the temperature started climbing above freezing yesterday, we started seeing the ice fall, crushing cars in Plano.
Unbelievable. You could see that over and over again and still almost not believe it. It's so crazy. Channel 8's Teresa Woodard has been following this for us. A lot of people actually being victimized by the ice here in Plano.
That's true. Shelley, Jason, it is incredible to see that video. And then this is what...
All right, I'm going to move on. You saw this one in the earlier clip, but I'm going to play it again. So we saw a number of videos that were kind of humorous, guys falling off roofs and all that sort of thing. But what you just watched on that small roof, it was a fair-sized bank of snow, that was somewhere between 6 and 8 tons of snow. And this is the thing people don't realize. You watch these videos and you know it's all kind of fun and all that. But that was between 6 and 8 tons of snow evacuating that small roof in just under 5 seconds. That can be a hazard, and sometimes the result is much more grim than just property damage. This article was on the Fox News website just last month. This happened very recently in Idaho, and 3 children were buried by a rooftop avalanche outside their family cabin, and one of those little girls was deceased. She didn't make it. So that's a little grim. Let's talk about the phenomenon of rooftop avalanche and why it happens and how it happens. During a snowstorm, usually the roof is super chilled. And what happens is that there is actually a frictional bond between the snow and the roof. And when I say, you might think of it in a sense, when you were a kid, you might have made the mistake of putting your tongue on a sled runner, right? And this is the same kind of temperature-sensitive frictional bond that takes place between a blanket of snow and a super cold rooftop. And so that bond holds the snow in place, and it piles up, sometimes many feet of it, on top of that roof. There's also a cohesive bond that takes place from the blanket on one side that's more or less glued to the blanket on the other side at the ridge. Now that bond is not nearly as strong as the frictional bond on the roof surface itself. Obviously, when this roof piles up with snow, it imposes a gravity load, or what we sometimes call a drag load, of the snow just induced by gravity and by the pitch or slope of the roof that's pulling this. So there's a force, obviously, that's trying to pull this bank of snow loose from the roof. And that drag load is being resisted by this friction here and that one up there. Now, when the sun comes out, and this, an avalanche can be precipitated in a couple of different ways. Either this load gets so great that it exceeds this frictional bond and it frees itself. But more often what happens is that the freeing of this bond is caused by sunlight. The bank of snow is to some degree translucent. And so the UV rays of the sun, which are the solar rays that warm objects, the UV rays pass through the translucent bank of snow, and they're absorbed by the roof surface, and they warm the roof through the bank of snow. So this can happen even when temperatures outdoors are well below freezing, because that roof surface is actually insulated by the blanket of snow. So even if the temperature in the air is sub-zero, the roof temperature can heat well above freezing from this absorptive effect of the sunlight. And so that roof becomes warmer now and goes above freezing. That temperature-sensitive bond that was once holding this snow to the roof is now turned to meltwater. The bond is freed, the friction is freed, and worse than that, it's converted this snow adjacent to the roof to melt. It starts melting. So now the roof is actually lubricated by the meltwater. This throws all the stress up here to that cohesive bond. And that cohesive bond is a fairly weak one and can rarely resist all that load that it's now experiencing, and the avalanche occurs. And it occurs usually in rather dramatic fashion, as you've seen in those videos. So that's the science of why rooftop avalanches occur and how they occur. So what is a snow guard? Well, a snow guard is a device or system that increases the friction between the roof and snow so that it's no longer relying on that temperature-sensitive bond, and it retains the snowpack on the roof so that it can evacuate the roof in a slow and controlled, predictable fashion rather than a sudden avalanche. How does it evacuate the roof? Well, it evaporates. It says here sublimation and thaw. Sublimation is a fancy word that just means that something can pass from a solid state into a gaseous state without ever becoming liquid. And so whether you knew it or not, a lot of snow sublimates. It goes away without turning to liquid. It just goes directly into an evaporation stage. So maybe you learned a new word today. I had to look that one up the first time I saw it. Snow retention devices date back hundreds, maybe thousands of years into the Alpine regions of Europe and Northern Europe, and was accomplished by a couple of different methods. Here you see stones that are placed on this Scandinavian roof to retain, and they're accomplishing the same thing. They're a means of increasing the friction between the snowbank and the roof. And you'll also see, dating back centuries of time, the use of logs to do the same thing. And so, in case this is gelling a little bit in your brain, cleats, individual units placed on the roof, or fences, continuous fence assemblies. And this goes back hundreds of years, perhaps a millennium or more. And here you see both. Here in this case, the logs are helping the stones stay there. I was real curious when I invented S5 technology, and of course, I invented that primarily because I was looking for a better snow guard. I was a contractor, like most of you, probably like some of you. I had used these plastic parts for years. It was what was available. They didn't work. I was frustrated. When I built my own home, I said, I don't want that crap on my roof. I got to figure out a better way. And that was actually what led to S5. But I was curious to see how snow retention was accomplished in some other regions of the world where it's been used for hundreds of years. This is an Alpine village in Austria, and you can see over there the evidence of an avalanche from years ago. And by the way, avalanches on the ground and avalanches from the roof have many, many commonalities. They're very similar in their behavior. But these people in these regions of the world have dealt with this issue for hundreds of years. And here you see, just outside that village, the two methods. Individual cleats, that's what these little triangles are, and fences, protecting, in this case, roadways. And both of these methods, by the way, can work and do work. It's not, they each have their own upsides and downsides, if you will. But they can both work when they're done properly. So here's some examples of protecting occupants. This entrance to this Pizza Hut, and you can see the snow looming up here. It's already tipping over this exhaust flue or whatever that is. But you can imagine you're the guy with the pizza pie coming out that door, and the door slams behind you. This is upstate New York. This is obviously a pedestrian walk, right? And see what's happening here. Imagine had someone been walking down that path when that avalanche occurred. Here, this is in my home city of Colorado Springs. It's a Denny's store and a Denny's restaurant. And just look at the trajectory of that roof to dump snow along the entranceways to this restaurant. And what is this right here? A handicapped ramp. So we're telling the poor cripples, wheel yourself up this ramp, and they are right dead in the trajectory of a rooftop avalanche. Same deal here. Here we are. This is a hotel in Colorado Springs, and the registration office is right through here. Notice, we're picking on the cripples again. So they get out of their handicap van, and they're wheeling their chair down through here. I was there with my camera. I was ready. And this guy was loading up this car, and you see this stop sign here. He got his car loaded, and he was right there at that stop sign when it let loose, protecting entryways. Now, a lot of times we have architecture like this, where, a portico that comes out and protects that entryway. And so people are supposed to go this way. But people don't always walk where they're supposed to. So what if they're going this way? Now, this one is equipped with snow retention. Not so here. That's what the sign says right out front here. And by the way, have you guys seen signs like this used? Right? One mentality is, well, I'm the building owner, and I know that there's a hazard there, so I'm going to put a sign to warn people, okay? A good trial lawyer will make a very good argument. You knew. It's proof that you knew there was a hazard because you put a sign out there. But what if somebody didn't read the sign? What if somebody couldn't read, et cetera, You know what this says, right? Same sort of deal. That could actually incriminate you more than it could help you as a building owner. And here, this is a great one, right? You're the guy. This is a bank drive up, right? So what do you do as you're pulling up there, right? You lower your window, right? But you see how that snow is behaving there. I mean, it's getting ready to let loose. And see it contrasted here. Now this is a portico, and this blanket is behaving itself. The clue is that's a little piece of color guard you see sticking out right at the end of that bank of snow there. Oops. Remember, when snow releases, we can very easily be talking about many tons of snow that come down. It ripped a couple of letters off there. There used to be an E and an R up there. Too bad for the Porsche. Protect landscape and building elements, okay? Those last slides had to do with pedestrians and vehicular traffic. By the way, I was called by one of our local news stations in Colorado Springs. The Olympic Training Committee had a deal with the city, and the city actually gave them a building downtown and then renovated it for them, and they put a new metal roof on the thing. The building was about 4 stories. And they equipped it. They did have snow guards on it, but they weren't the right way. And it shut down the busiest intersection in Colorado Springs for 3 days while they tried to figure out what are we going to do with this. And they called me because I was a local consultant concerning snow and ice and so on. And I was the lead story on the 5 o'clock news that night. They were interviewing me about this thing. It was a real political hot potato because the city had given the Olympic Committee this building and paid to renovate it and put this new roof on. And there were a lot of citizens who thought that maybe they shouldn't have gone that far. So it was really a political hot potato. And then they were talking about the architect was deficient, defective design, blah, blah, blah. So a little bit too late for this. Do you see that this might cause a problem for the glass here, not to mention the little landscape? Here it's a little too late. See what's going on here? That's that same Pizza Hut. Protect building and roof elements. How much of this kind of thing will a rooftop flue or vent stack survive? There you see some aftermath on a soil stack. There you see some more. Soil stack in this case is gone. Here you see these 2 hangy downy things there. That's where the rooftop lights used to be. Now they're down here. At valleys, you see what snow and ice has done to these seams when it migrates down that valley. And over here, it's actually dislodged the panel seam and pushed those panels about 4 to 6 inches in that direction, just the force of snow migrating down that valley. And here you would wonder, okay, when it pushes those panels over that way, what exactly does the rest of that roof look like? That's what it looks like. That detail we were just looking at is down here. So, I don't know, that's probably $15,000 worth of damage or something like that. Here you can see that it's ripping the fascias right off this roof. There you can see the aftermath. Again, in this case, it was a continuous panel, with a fascia break there. It was a continuous panel from eave to ridge within this fascia break. I don't know how many tens of thousands of dollars worth of damage was done here. This one is at Lake Tahoe in Nevada, but you can see the damage through the valley here where it's laid over the seams and ripped the gable flashings loose. This particular job was involved in a $20 million lawsuit, all different problems precipitated from a lack of using snow guards. I know that may be hard to imagine. The roof claim, replacing all the roofs, this was one small area on a very large complex, but the roof part of that claim was only about $2 million. The rest of it was that when the snow fell off the roof and piled up below the eaves, and then there was more melt and thaw and so on from above, and you can imagine a pile of snow under the eave like this, and of course a little bit of a trajectory, so it's out a little ways from the eave, but right near the building wall. And now the snow starts melting in the spring, and the melt water runs down, and it hits this side of that pile, and it's directed right into the building foundations and through the building walls. And so a huge part of that claim was replacing wall materials. They had all this mold abatement stuff going on because the moisture stayed in the walls and cooked and created mold. I mean, it was a mess. It was a $20 million lawsuit. Same sort of deal here. This was a Federal Express hangar building in Anchorage, Alaska. And the same thing was going on here where the snow was, this roof above, it's hard to tell from this photograph, but that eave line is 60 feet up. The ridge line is about 100 feet. It's a pretty large roof. And when the snow avalanched off the eave, it fell on the ground. This canopy that you see here wasn't there. But the snow fell on the ground, and so much snow dumped on the ground that it was actually imploding the walls. Well, they were metal walls, they were kind of fragile, but it was imploding the walls. And so they built this long canopy structure on both sides of this building at a cost of $240,000. This is 12 by 12 by 3/8 thick steel tubing with a 3/8 inch steel plate. And that was just so that when the snow cascaded off here and it built a huge thing, that it stayed away from the building wall. $240,000, about $20,000 worth of snow retention would have cured their problem. Here you can see there's a valley going up here to your right. So you can see what the snow did when it came down that valley. And here, the difference, so here you have an adjacent wall. So you have a lower roof and then an upper roof. And the height difference there is about 12 feet or so. And so you can see that the snow came off that upper roof and landed on the lower roof. It looks like no big deal until you look underneath and behind the point of impact here, and this is what you see. Now, this roof was the first winter that this lower roof had endured. And that lower roof, notice that this is at the top of that roof, so the slope is down this way. This entire roof had to be replaced. It was a year old at a cost of $30,000. About $3,000 worth of snow guards would have prevented the damage that you see there. Are there any reasons not to use snow guards? Well, yes. If no real hazard is present, it could be a needless expense. And this is an interesting one. You've heard, well, we don't want to hold snow on the roof because it could cause a structural collapse. In most cases, that's actually a myth. Roofs are generally designed in such a way and engineered that they do not anticipate that snow is going to evacuate the roof. Most building designs presume that the snow is going to stay on that roof all season. But if there is a provision in ASCE 7 called slippery roof load reductions. And if the building engineer, the structural engineer, uses that provision in ASCE 7, he is allowed at a certain pitch, I believe it's like a 712 or something like that, he is allowed to reduce the load on that structural design, presuming that the snow is going to evacuate because the roof is steep enough. There are a whole list of other caveats to be able to use that. But every self-respecting engineer I have ever spoken with, and I've spoken with quite a few, when I ask them, do you use this slippery roof load reduction thing when you design structures? I've not found one who has said, oh yeah, we use that. And quite to the contrary, they're kind of this way. No, well, I'm not touching that. So, but if the engineer did use that load reduction in his structural design, it could be an issue. If the building structure is designed appropriately, it should never be an issue. But if the structure is under-designed to the service loads to which it's exposed, or in other cases, if you have unanticipated and very severe icing, ice can overload a roof more easily than snow. I know in some of the mountain communities in Colorado, they go out there and they shovel their roofs. But if that is an issue, if somebody just, we want the snow to come off, then obviously you don't want to use snow retention. Yeah, they do. They call it drop zones. So architecturally, they've planned the building walls are durable enough that they won't implode the walls, and that's quite an architectural process to plan what they call a drop zone to enable the roof to come off enable the snow to come off the roof. You really don't want the roof to come off, and then have a dedicated zone that's protected where it can't hurt anybody.
And then the roof should be designed then too, correct? That you're not going to end up with a bunch of valleys or slopes.
Yeah, see now that's an interesting point, what you just said, because I touched on this slippery roof load reduction very briefly, but I mentioned that there's a long list of caveats to the use of that load reduction, and that's one of them. That the roof geometry has to be such that it enables snow to slide freely off the roof, and there can be no obstruction on the roof that prevents that. So as soon as you put a dormer in the roof, King's X, that roof doesn't qualify anymore. There are also, believe it or not, insulation caveats and building occupancy caveats to that provision, so that it says that the building must be a heated building, because what they're counting on is building heat escaping through the roof assembly and freeing that bond that I spoke of earlier. They're counting on building heat being able to do that to make the snow slide off. So the building has to be heated. That's one of the caveats. An obvious issue with that is, okay, we have a neighborhood mom and pop grocery store, big grocery store, and it's a conditioned space, it's a heated building. The big huge Kmart chain moves in, or one of the big huge supermarket chains. This happened in my hometown. And the mom and pop is forced out of business, close the store, board it up, prepare it to sell, turn the heat off. Now it's not a heated building anymore. What happens to the roof? Now it's in danger of collapse, perhaps. So there are, and then the insulation requirement relates back to that. There's another caveat in that code language, in that standard, that says, because we're counting on the heat escaping from the building and warming the roof and melting the snow and so on, now, we want to be sure that the heat escapes. So we have a maximum R value allowed in that roof of R22. It's either 22 or 23. I think it's 22. Maximum. You can't insulate your roof more than R22. Then on the other hand, they say, now, if too much heat escapes out of this roof, it's going to melt the snow and it's going to run down to the eave. We haven't talked about ice dams yet here, but we will. And it's going to form an ice dam. And an ice dam is an unintentional snow guard. So now we've shot ourselves in the foot. So believe it or not, that engineering standard says thou shalt have a maximum of R22 insulation and a minimum of R19, because we want some heat to escape through there. Another obvious dilemma: what happens when the building occupant, whomever it may be, after the building sold 2 or 3 times, he doesn't know what goofy standard the engineer did, and he's tired of his high heat bills. So he wants to retrofit some more insulation up there. These are the glitches within that engineering standard that most engineers, that's why they do this and say, we're just not going there.